And as usual, I picked out some. I'm working from the key. And there's a key in Brightspace for the review document that I gave you. And plus you've got the work problems. But if you want to, as we go through, you could write down the key to every answer, not just the ones that we're working on. But I'm only going to stop at the ones that are highlighted, unless you see one that flips a switch and you need some extra help on it. Then just stop me and we'll work on those too. Which of the following general reaction types is characterized by there being a single reactant? Remember, reactants on the left, products on the right. So a single reactant would be something, say, like AB. So what's it going to do? The only thing it can do is decompose. Right? It can decompose into A plus B. So the answer is B, decomposition. About 4. Proper assignment of oxidation numbers to the elements in the polyatomic SO3 2- would, let me see if I can get that out of the way. Come on. There we go. Would be SO3 2-. When we're assigning oxidation states for each of the elements, there's some that that you're given. You're assumed to be a certain value. Otherwise, you can't calculate the others. And remember, the total for a polyatomic ion has to add up to that 2-. So the way I do it, we know that oxygen, as long as it's not in a peroxide, if it's in a peroxide, then it's a -1. But any other place it's in a compound, it would be a -2. Times 3 is -6 total charge. That has to be accounted for. But we only have to neutralize 4 of those because we're going to keep 2 of them out for that 2-. So we only have to neutralize a -4, which makes that sulfur +4. So it'd be +4 -2. Okay. When students are first exposed to this type of calculation, sometimes I see their eyes roll back in their head and their head spin around and I haven't seen any vomit green stuff yet. They look like they're possessed. Practice will get you over those problems.
Well,
yeah,
on 4.
Yeah.
You said it's +4 -2. That's because there's 3 oxygen atoms, correct?
Correct.
So you do it for the base, not the total of the.
You start off, -2 is given for oxygen in a compound. So you start off with -2. But if each oxygen has a -2 oxidation state, that totals up to a -6.
Yeah, but whenever you're asking about the oxidation numbers, that doesn't matter. What the total number of atoms is doesn't matter.
Yes, that's true. The answer would be just the oxidation state for an individual. Yes, that's true. Okay, number 6. Which element is oxidized in the following redox reaction? So we got 2 hydrogen sulfides plus oxygen yields water and sulfur.
It's 2H2. Okay.
2.
Your head was in the way.
Oh, that happens to me a lot. Okay, so which element is oxidized? Remember that'll tell them apart. Oxidation is loss of electrons. Reduction is gain. So which one of the lost electrons? Right. In order to do that, we've got to do the oxidation states and say what happened across that arrow. elements are going to be zero. That oxygen is a -2, and that hydrogen's a +1. Over here, hydrogen is a +1, so that means this sulfur has to be a -2 to balance. Okay, now we can follow the electrons. This sulfur would go to -2 to 0. So how did it get there? It had to lose 2 electrons, didn't it? 2 electrons per sulfur. And hold on a second. That thing's not balanced. Right? 4 hydrogens, 2 sulfurs, 2 oxygens. Oh, let me see if I can correct that in here. Where's my, here it is. That needs to be 2. There we go. Come on. I don't know if I made that mistake or it came out of the question bank like that. Okay, so we found out which one is oxidized. That means this has to be oxidized. Right? Hydrogen sulfide is oxidized. In fact, the sulfur in the hydrogen sulfide is oxidized. So that means if you've got an oxidation going on, you have to have a reduction going on. So just to be complete, right, that oxygen would have to gain 2 electrons. Per oxygen times 2 oxygens equals 2 electrons. You know, there's something wrong with this. We better balance this thing again. I mean, it looks balanced, but the electrons are not coming out right. Because 2 sulfurs times 2 equals 4 electrons. And then 2, yeah, that comes out right. I don't even know my own math. That's okay. You got to have the same number of electrons oxidized as you do reduced. So yeah, it's balanced now. Okay, that was number 6. My WD-40 is working. That's the way you renovate a board. Clean it real good with isopropanol and then go over it with light coating of WD-40. It erases real nice. Okay, number 7. Which substance functions as a reducing agent in the following redox reaction? Okay, we've got a combustion reaction, right? Anytime you have oxygen in there like that. And it's going to make carbon dioxide and the water, I would be willing to bet. So we need 2 of these, 2 of those. Okay. Which one functions as a reducing agent? The reducing agent is the one that causes the oxidation, that causes the reduction in other species. So it has to be oxidized. So we're looking for the one that's oxidized. That's 0. That's a -2, -2. So this would be -4 plus 4 there. That's a +1. 0. This is +1, so this would be a -4 for that one. So carbon would go from -4 to +4, which would be how many electrons? 8, yeah. It would have to lose 8 electrons per carbon. We've only got 1 carbon. So a total of 8 electrons. Then this oxygen is going 2 different places, actually. It's going here and here. Right? Fortunately, they're both the same oxidation state. Right? So we're going from 0 to -2, which means we gain 2 electrons per oxygen. And we got 4 there, 2 plus 2, that's right. Times 4 would be 8 electrons. We're good. So if we gain, let's see, we're looking for the reducing agent. Which one's oxidized? Oxidation is loss. This is oxidized. So it is the reducing agent. It's the one that caused the reduction over here. Okay, so methane, A, that's right. That's the reducing agent. Oh, okay. I'll just put 8 down here. Got a new 2 CH203. 2 CH203. This illustrates the point that you got to pay attention to your cases. Uppercase, lowercase. If I made that an uppercase, we would think that's carbon dioxide plus another 3 oxygens, right? But this is cobalt plus carbon yields what? 4 cobalt, 3 carbon dioxide. Cobalt, 3 carbon dioxide. Okay, what's the question? What's the change in oxidation number for cobalt? All right, that's 0. That's 0. And cobalt is going from, let's see, we've got a -2 here, -6 total. So that means we have to balance that with a +6 over here, but there are 2 of them. So each one has to be a +3. Okay. So we're going from, get those out of the way. We're going from a +3 to a 0 on that cobalt, which means we had to gain 3 electrons per cobalt. Right? Times 4 equals 12 electrons total. So cobalt is reduced, and the change in oxidation number is -3. It went from a +3 to 0. +3 to 0. Yep. All right. All right, number 12 and 13. 12 and 13. The minimum combined kinetic energy reactant particles must possess in order for their collision to result in a reaction is called. That's just definition. Right. Any ideas? Well, without looking at the answer, of course. It's activation energy. Right? Have I drawn this thing for you before? Progress of the reaction that way. And this is energy of all the reactants and products. So if we start off here, we go like that. Right? This is the reactants. These are the products. And you got to have a certain minimum amount of energy from here to here. That's the activation energy in order for the reaction to proceed. And you can also tell from this graph that this is an endothermic process. Right? You got more energy in the products than you do in the reactant, so it's stored energy in the products. Energy went in, didn't come out. But to answer the question, that's activation energy. Is the minimum combined kinetic energy that is required for the reactive particles to get over the hump. Right? Sometimes this is called activated complex. Right? You've got to reach that point before it'll go down the other side. All right. 13. Whether a reaction is exothermic or endothermic is determined by. Oh, I should have left the graph up there, huh? It's not determined by the activation energy. The values of, let me just put it back up. Sketch it. Let's sketch it in this way now. That's the same as before, wasn't it? The amount of energy that you start with, the amount of energy you end up with, these parts of the graph here and here, these are equilibrium. Doesn't matter how you get from here to here, as far as the rate of the reaction is concerned. This part is kinetics. This determines the rate of the reaction. But this is what's the energy cost or what's the energy return? In this case, the energy cost gets you from here to here. That's endothermic. If we do it the other way around, or if you go backwards, which reactions can do, if you go backwards, then you get energy back. And that's an energy output. All right, so to answer the question, the exothermic or endothermic values for a reaction are determined by how reactant and product potential energies compare. Right? Is it like this or is it like that? All right, 14, 15. Which of the following changes is most likely to decrease reaction rate for a chemical reaction? For the chemical reaction. 2 carbon monoxide plus oxygen yields 2 carbon dioxide. Okay, we're talking about decrease reaction rate. Rate. So what are some factors that will change the reaction rate? Temperature. Temperature will change the rate. How about, will the reaction rate change if we add something on one side or take away something on one side? No, the rate won't change. The reaction rate won't change. The equilibrium position will change. Right, that's Le Chatelier's principle, which we didn't get to do today. But if you are at equilibrium now, that means the forward rate and the reverse rate are equal. That's what happens at equilibrium. It's still happening, right? Microscopically, you still got that reaction going this way and this one going that way, but they're happening at the same rate. So it looks like there's no change in the concentrations of reactants and products. So in order to change the rate, you need either change the temperature, right? Changing the amount doesn't change. Let's see, where am I? 14. Adding a catalyst, yeah. Catalyst will change the rate also. Temperature and catalyst will change the rate. But now why does it say remove some CO from the reactant? Okay. All right, I have to start thinking like the authors. Right? You can't think like a chemist. You have to think like the authors. So if we want to decrease the reaction rate, the apparent reaction rate, I would say, what we actually see, then if we're at equilibrium and you remove some, well, actually, you don't have to be at equilibrium. If you have less carbon dioxide, that means the encounters of the reactants are less likely, less probable. So you were probably on track, right? You were thinking like the authors and I wasn't.
Honestly, like burning something, if you remove some oxygen, it's not gonna burn.
Slows it down.
Yeah.
Yeah, that's true. Yeah. Okay, so if we remove some carbon monoxide, then the reaction, you're not going to have enough to react with the oxygen, so it'll slow down. Yeah, okay, I guess that's all right. At least that's the answer that's given. And the others, adding twice as much O2, that would speed things up. Tripling the temperature would speed things up. Add a catalyst, speed things up. That's not a good question, but at least we know the answer that the authors are expecting. Let's put that one in my rear view mirror. Row number 15. Okay, catalysts are correctly characterized by each of the following statements except one. All right. All right, so they can be either solids, liquids, or gases. Oh yeah, that's true. They can be any phase. They lower the activation energy of a reaction. That's also true. They lower the activation energy by providing an alternate pathway for the reaction to occur that requires less energy. They participate in the reaction, but they're not consumed by the reaction. They go in one side and they spit out the other side, apparently unchanged. C, they do not actively participate. That's false. They do actively participate, but they are not consumed. Right. So C is the answer. That's the one false one out of those statements. All right. Oh, we're going to write an equilibrium constant for this reaction. Okay, 17. And we're working with HCl and O2. And they're all gases. So what do we got? 2 waters and 2 chlorines. So this must happen at a high temperature in order to keep water a gas. Okay, so how do we express the equilibrium constant for these? It's the concentration of water times the concentration of chlorine to the powers of the exponent. That's in the numerator. The denominator has the reactants. So we'll have hydrogen chloride to the 4th power and oxygen to the 1st power. There you go. Yeah, C, that works. And how long it takes to get there? If you start off with only oxygen and only hydrogen chloride, I don't know how fast it'll happen. This only talks about once it gets there, that's a constant. And this is only constant for a given temperature, right? And no catalyst. Okay, change the temperature, you change the equilibrium constant. All right, 17, 18. Le Chatelier. Definition. What is Le Chatelier's principle? Right. But just put it in your own words. You're starting with a reaction at equilibrium. And now you're going to do something to stress that system. So when you stress it, what's the system going to do? It's going to respond to reduce the stress. And it depends on the reaction. It depends on the stress applied as to what its reaction is going to be. So let's see which one of those fits. Only exothermic reactions can reach equilibrium. I don't think so. Only reactions in which a catalyst is present can reach. No. If a chemical equilibrium is disturbed, we stress it, the system will try and reestablish equilibrium. That's as good as any. Right. So how does it do that? Well, it depends. If you have reactants and products that are gases, you can change the volume. Right. But in that case, if you change the volume, the only way that amounts to a stress is if the number of moles of reactants and the number of moles of products are different. If they're exactly the same, you can change the volume all day long, it won't do anything. How about temperature? Change the temperature, that's a stress, right? How does that stress, how is it relieved by a reaction? No idea. It depends. Is the reaction endothermic or exothermic? Right. If you have reactants and products, if it's endothermic, then the heat goes in this side and is stored in the products. So when you raise the temperature of this one, you're increasing the amount of heat. And if you view it as a reactant, increasing this shifts it to that direction as a response. But if it's exothermic, and we put the heat on that side, then you increase the temperature, it's going to shift it back the other way. Okay, so temperature depends on what type of reaction it is, exothermic or endothermic. What are some other stresses? Well, any type of reaction where you change the concentration of reactants or products, that will affect the equilibrium. It won't affect, you can change, if the reaction has a solid in it, either a reactant or a product, you change that one, no effect, because solids don't change concentration. Pure liquids, same thing. Right, if we have a reaction in aqueous solution, and the water is part of the reaction, I guess if you add more water as a solvent, then you would change the concentration of the other reactants and products, and that could have an effect. But all pure liquids and all pure solids, you can change their concentrations all day long. It won't affect the equilibrium. Only solutions and gases, you can change their concentrations and that will shift the equilibrium. Now, when you do that, as long as you don't change the temperature, the equilibrium constant is a constant. When you change the temperature, what you're actually doing is changing the equilibrium constant to get it to shift. But that's theoretical and underneath Le Chatelier's principle. Okay, rattling on, and which one were we up to? 19? Okay. Carbon dioxide and hydrogen are allowed to react until an equilibrium is established as follows. What will be the effect on the equilibrium of removing CO from the equilibrium mixture? Well, since it's up there, I don't have to write it, do I? If we remove a product and the product is a gas, they're all gases, that's good. We remove CO, then the reaction as written is going to shift to the right to compensate for the loss and reestablish equilibrium. Now, that's another thing that by not having the lab today, I'd get a chance to hammer this point. If you say a reaction is shifted left or right, and you don't have a balanced equation to work from, it doesn't mean anything. You have to base right and left on a balanced equation. Okay, just word to the wise. Excuse me, 20. Le Chatelier again, okay. Which of the following changes will shift the position of the equilibrium to the left for this reaction? All right, this is the Haber process. We take nitrogen, add hydrogen, and make ammonia. And it is exothermic. So we put the heat term on the right. Now, which one of these will shift the position to the left? Right. Well, if you double the concentration of nitrogen, right, that increases the nitrogen concentration, it's going to shift to the right. If we decrease the concentration of ammonia, we're removing a product, it's also going to shift to the right. If we increase the concentration of hydrogen, that'll shift to the right also. You're changing its concentration, then the shift is going to consume some of it, not all of it, but some, until equilibrium is reestablished. And D, if you triple the temperature, you're adding that heat term on the right. So if you view it as a product, you add product, it's going to shift to the left. So D is the answer. And that was Haber's problem, right? He knew that the reaction had a certain activation energy to get that nitrogen and hydrogen to work. So he had to increase the temperature to about 800 degrees Celsius. And then he increased the pressure to several atmospheres so that we'd have more frequent encounters, impacts for the reaction. But he also knew that the reaction was exothermic, and when he did that, the reaction was going to try to shift to the left. So in order to get it to go for the speed of the reaction, to give him some product, he introduced a catalyst, finely divided iron. And then that wouldn't change the equilibrium problem because of the temperatures governing that one. But what he did was he recognized that in the reaction vessel, nitrogen, hydrogen, and ammonia are all gases there together. So we would just bleed off, continuously bleed off reactants and products together. Run them through a cooling cycle. Ammonia will condense at a higher temperature than nitrogen or hydrogen. So he condensed out the ammonia and then took the gas products, the nitrogen and hydrogen left over, and ran them back through. So he just kept bleeding off ammonia. And that also shifted the reaction to the right because he was removing product. So he eventually got the efficiency up enough to where it would pay for itself. And I think that in the beginning amounted to about 15%, which doesn't seem like much, but it was better than the theoretically expected. That was Haber, and then Bosch came along and scaled it up for industry. So you'll see it called the Haber-Bosch process sometimes. I wonder if that's the same Bosch that started Bosch and Lomb Company. I don't know. Could just be a family business. 22. All right. In which of the following compounds does chlorine have an oxidation number of +5? All right. So we got 3 choices, and then we got more than one and none. Okay, so let's say we just look at A, B, and C. Find out what the oxidation number for that one. If that's an aqueous solution, that would be hypochlorous acid. And potassium chlorite and calcium ClO3 chlorate. Okay, oxidation number of +5. Well, let's see. We're given that hydrogen is +1. Right. When is hydrogen not +1? Remember that rule? When it's combined with a metal. If it's combined with a metal like this one, an aluminum hydride, then aluminum is the +1 and hydrogen is, the negative one. But when it comes first like this, you can assume that it's +1. And oxygen's -2. So together we have what? A -1 total? That has to be balanced by a +1 chlorine. And to check yourself, you can say -2 +1 +1 0. Neutral compound has to be 0 total. So that's not it. How about this one? -2 here and a +1 there, right? All alkali metals are +1. So that's a -4 and a +1 is a -3. That means this one has to be a +3. Okay. And for this one, let's see, calcium is an alkaline earth. It's a 2+ charge. Oxygen is a -2. So we've got a +2 here. We got 2 times 3 is 6 oxygens times a -2, which is -12, right? 2 times 3 is 6 oxygens at -2 each. It is a -12. So that's together is -10, right? Well, we've got 2 chlorines, right here. 2 chlorines, each one has to be a +5 in order to balance that -10. Okay. Now that's one way to do it. The other way is say, all right, I know this is an ionic compound, and I know chlorate is that. So you can do it with just this part and get the same answer, right? -2 times 3 is -6. Right? Pull one out, -5 +5. So it works either way. That would be C. C is the only answer. So E's not right and D's not right. Has to be C. All right, let's scroll a little bit. We've got quite a few in a row here, 23. Okay. Which of the following sequences of sulfur-containing ions are the ions arranged in order of decreasing oxidation number? So when they say decreasing, it could be like we went from +5 to 0 to say -5. That would be decreasing. So it could be a -1 to a -5 would be decreasing. Or a +5 to a +3 would be decreasing. Okay. So let's see, what do we have here? I'm just going to put the ones that were given. Sulfite, sulfate, and sulfide. Sulfite, sulfate, sulfide. What else? Thiosulfate. And that's it. So these are the only ones that we have to determine the sulfur oxidation number. All right, so this is -2 times 3 is -6. We hold 2 of them out. So -4, we have to balance with a +4. Okay. This one is -8. Hold two of those out, -6. This is +6. This is a -2. -2 times 3 is -6. Hold 2 out. -4. +4 total, +2 for each sulfur. So a decreasing oxidation number would be this one. Let's see, is that what they say? Sequence, range and order of decreasing oxidation number. So this one will be the highest one. Then we'd have this one. Then we'd have this one. And then we have this one. So each one has 3, right? So it's either this one or that one. So let's see, SO42 minus is B. And then if we go, well, actually, we can leave this one out and go to that one. Go to this one. That one works. B works. More than one, correct? Let's
B.
Huh? How about A? There, oh, went the wrong direction.
Yeah.
Huh?
I
Yeah.
didn't.
And C, this one, oh, wrong direction. Okay, so B is the only possibility. Okay, 24. Which of the following reactions is a non-redox reaction? All right. There's just 3 of them. Okay. Calcium carbonate. Run it through a kiln. Get calcium oxide plus carbon dioxide. That's how they make concrete. They just take calcium carbonate, ground it up, run it through these huge kilns, constantly turning, and they're blowing super hot air through them. Then 2 potassium chlorate yields 2 KCl plus oxygen, right?
3 oxygen.
3. Okay. And then SO3 plus H2O yields H2SO4. Okay. All right. So this one's easy. Rule of thumb. If you've got an element on one side and it's in a compound on the other side, that's a redox. Unmistakable. This one we have to calculate. All right, so if we go from, let's see, calcium's always 2 plus. That's, let's see, oxygen's -2, so that was okay. -2. So this would be +4, correct? And this would be -6, and +2 is -4. This would be +4, right? So that's non-redox. Nothing changed. Calcium's the same, carbon's the same, oxygen's the same. How about this one? -2 plus 1, -2, -2. So this would be a -6, this would be a +6. And this would be +2, this would be -8, -6, +6. That one didn't change. This is non also. All right. So more than one is non-redox. These 2. So that's why D is the answer. All right, 25. I got happy with a highlighter here, didn't we? Which of the following statements concerning oxidation reduction is correct? All right. Well, let's see. Since we got more than one correct and no correct, then we have to do all of them. Have to do all three, just to be sure. How about A? They cannot occur independently of each other. That's true. They always occur in pairs. Oxidation reduction, that's why we put them together. So that was true. They accompany all chemical reactions. That is false. We just proved. I mean, you just have to show one exception, and that statement's false. C, they describe respectively the gain and loss of electrons. Oxidation reduction. No. This is the loss. This is the gain. All right, so I got it backwards. All right, so A is the only correct answer out of that group. Okay. All right. 26. In the redox reaction, they tell you it's a redox, and they're right. We got iron on one side, oxygen on one side, and they're in compounds on the other side. So that definitely redox. We're looking for a reducing agent, oxygen, substance, oxidized, as a whole gamut. So we need to assess this reaction for all of its components. Let's see, FeCO3. Is that water? Yep, 6,4. Oops. I was looking at the wrong one, but about 3. I left out one.
HCl.
Yeah. Okay. Okay. So 12, 3, and 4. Well, 3 and 4. There we go. Okay, so these are elemental, they're zeros. This one's easy, -2 and +1. We don't have a rule for chlorine. We do for fluorine. Fluorine is always -1, no exceptions. But when you're stuck with, well, this one will be easy because hydrogen's +1, that makes this one -1. But when you're trying to figure out what this one is, we go to chlorine, say it's -1. So that means this is +3. And now we can assess what happens to iron. It goes from 0 to +3, right? Loss, 3 electrons per iron times 4 of them equals 12 electrons total lost. So this is the oxidation step. And it's also the reducing agent. Okay, oxygen goes from 0 to -2. Hydrogen doesn't change, chlorine doesn't change. So this is a gain of 2 electrons per oxygen. Times how many? 6? Times 6 equals 12 electrons. That's good. We balanced our electrons. Okay, now we can answer the question. HCl is the reducing agent. No, iron is the reducing agent. Oxygen is the oxidizing agent. Okay, E, O2 is the substance oxidized. No, it's reduced. Reduction. All right, so that was not right. Iron undergoes an oxidation number decrease of 3 units. It goes from 0 plus 3. It's an increase in oxidation number. Right, so that one's false also. Oh, there are no correct ones. They're all wrong. Let's see, 27. In a redox reaction, the oxidizing agent is the substance reduced. Right? It gains electrons or it's reduced. Contains an element that undergoes a decrease in oxidation number. That means it becomes more negative. It could go from high positive to low positive, or it could go from positive to negative, go from positive to 0. But a decrease in oxidation number signifies reduction. And that's the oxidizing agent. So C is the answer. #28. For a collision between molecules to result in a reaction, molecules must possess a certain minimum energy. I thought we did this one before. Oh, and. All right, we did the minimum energy part. And exchange electrons? Not necessarily. Exchange means total transfer. It could be they share electrons. All right, so A can't be it. Interact with a catalyst for at least 1 second. Suppose there are no catalysts around. Have a favorable orientation relative to each other when they collide. That's the one. All right, you need 2 things. You need energy of impact, right, to provide that activation energy. And then they have to be oriented correctly for the transition state to start to form. They have to be oriented so that the bonds from the original start to break and the new ones start to form. And the orientation dictates that. So C is the correct answer for 28. How about, let's see, I blew by those in case you wanted to write them down. 29 through 31. We're only going to stop on 31. Chemical equilibrium is reached in a system when? When the concentrations of the reactants and products, their respective concentrations, don't change. Or that's the macroscopic observation. Microscopically, when the forward rate equals the reverse rate. Right, is that what it's looking for? Yeah. Reactants are being consumed at the same rate they're being produced. That signifies equilibrium. Let's see, this one can be A and C. Maybe that's why I didn't pull that one up. Okay, 34. Let's just make this one into a 4. According to 3. I'm sorry? 33. 33 was D. According to Le Chatelier's principle, which of the following effects will occur if ammonia is removed from an equilibrium mixture governed by the equation? Well, it's going to shift to the right, so that'll decrease nitrogen, it'll decrease hydrogen. Excuse me. Yes. And concentration of nitrogen will increase? No. Heat will be generated. Yes, because it's exothermic. So if you remove some of the ammonia, it's going to force the reaction to go to the right. and produce heat as a product also. So B is good. Concentration of hydrogen will decrease. Yeah, that's true also. So more than one correct response, B and C. All right, 35. I need a hook to hang my rag on. For which of the following equilibrium systems will the equilibrium position shift to the left when a stress of increased pressure from a volume decrease is applied? Okay, so let's see. We've got three to work from, A, B, and C. Okay. 2 NO2 and 7 hydrogen. NO2 plus 7 hydrogen is going to produce 2 ammonias and 4 waters. Okay, second one, carbon dioxide and water.
The first, carbon and that, it doesn't have a 2 after. Is it supposed to? The one that you just done be on here, it doesn't have a 2.
Thank you. Carbon monoxide. Product is carbon dioxide. And what? Hydrogen gas. Okay. There we go. That'll make a difference. Well, actually, for this problem, it won't make a difference. But we do need to be accurate. Chlorine, HCl, chlorine. And 2 HCl gas. Okay. All right. Which of the following will shift to the left when increased pressure by volume decrease? So if we're going to decrease the volume, which according to Boyle will increase the pressure, we'll squeeze it. Which one is going to shift to the left? To answer that question, all of these are gases. So we add up the total number of moles, 9 moles here, 8 moles there. 2 moles here, 2 moles there, 2 here, 2 here. You know what? None of them. Right? Change the pressure by volume change will not affect either one of these because they got the same number of moles of gas on both sides. And this one, you got 9 moles on this side and 8 on that side. So when you squeeze it, it's going to go to the right. It's going to try to make fewer moles to decrease the pressure. Right? So none of those work. Right? Easy answer. There's no correct response. I did all that work for nothing, huh? Okay, that was 35, 39. Okay, for this one, we're going to take parentheses 1, 2, and 3 and find out which of these are true. All right, so let's see. 1, 2, and 3. The only information needed to write an equilibrium constant expression is a balanced, excuse me, is a balanced chemical equation with physical state information for the reaction of concern. I'd say that's true. If the equation's balanced, that'll give you the coefficients. And if you have the phases, then you'll know whether you can include all of the terms. Because if you have solids and liquids in there, they don't enter into the equilibrium expression. Right? Only those that can change concentration. And for our purposes, that's aqueous components or gases. Right? So one is true. The oxidation number of sulfur is the same in the species H2SO4 and SO4 2-. That's also true. Notice in an H2SO4, part of that molecule is SO4 2-. All right, so you're talking about the same sulfur, actually. All right, you can go in and calculate it if you want, but I bet you'll come up with, let's see, what was it, +6.
The hydrogen.
There's always +1, yeah. 3, increasing the concentration of a reactant makes collisions between the reactant and other reactants less likely because of more crowded conditions. Nope, it's the other way around. It makes a collision more likely because there's more of them. Right? It's a probability statement. You have more molecules, you're going to have more frequent collisions. Right? So 3 is false. That means 2 of the above, B, are correct. Let's see here. There's another one. Oh, I skipped over those others. You want me to slow down? Let's go back. There we go. All right, you get 40 C. Okay. And then we got 41 is A, 42 is C, 43 is D. Okay. 44 is B. And we're going to stop on 45. Okay, so 1, 2, and 3. See if we can find the true statements. Of the known atmospheric greenhouse gases, carbon dioxide is both the most abundant and also the most efficient at preventing heat loss from the earth. Neither of those statements are true. Carbon dioxide is not the most abundant greenhouse gas, and it's not the most efficient at preventing heat loss. So that one is false. Regardless what the IPCC says.
It's ozone solution.
Right? Ozone does have an effect.
No, I meant the most abundant
Oh, the most abundant
greenhouse gas. I thought it was, where's the water vapor?
water vapor. Yeah. Now, water vapor is not the most efficient, but it's the most abundant. The most efficient probably would be something like methane.
That's what I thought.
Yeah. So 1's false. 2, ozone is a form of oxygen in which there are 3 atoms per molecule. That is true. Right? That's ozone. Ozone's primary purpose is to absorb ultraviolet radiation before it gets to the surface of the earth. You know, it protects plant life and animal life from getting burned to a crisp. But it's not long-lived. Right? It comes and goes really quickly. So we need a constant input of ultraviolet light that causes elemental oxygen to dissociate, and then the free radical combines with another oxygen molecule and makes ozone. But they disappear as quickly as, so if you have something that interrupts that process, then the ozone will start to deplete pretty quick. And that's the problem with chlorofluorocarbons, freons. They get up there and interrupt that process. They act like catalysts. That's what they are. Yeah. Okay, so 3 then. A decrease in body temperature slows down the rate of chemical reactions. Yeah, that's true. So we got 2 of the above are true. Yeah, B. Right? I mean, we are biochemical machines, right? Chemical reactions respond to temperature. Only the catalysts that make the reactions possible in our cells are unique. They're not like inorganic catalysts that can go forwards and backwards at essentially the same rate. Enzymes function within a narrow temperature range, and they usually, not always, but usually catalyze in one direction only. So if you need to go the other direction, you need another catalyst. And that allows the cells to control the reactions. Right? If it wants the reactions to go forward, it only gives it that catalyst, that enzyme. Now, there's some notable exceptions that are problematic. We won't go into that. Oh, and that narrow temperature range is important because if you get too cold, then the enzymes don't work efficiently. I mean, they're less efficiently than inorganic catalysts. If you go too high, then since most of them are proteins, you'll denature the protein and it won't function anymore. So when you've got a fever and it gets up 104, 5, 6, what you're doing is you're destroying your enzymes. They don't function. Among other, that's one of the things that happens. Okay, so yeah, B is the answer, right? Yeah, B is the answer. Let's see, 46. Assign the following reaction to one of the reaction classifications given the list. Okay. If you've got 2 reactants and you make 1 product, that's a combination reaction or a synthesis. So your choice is, combination is the only choice, so that one works. Okay, let's see, 47, 48, 49. Okay. Following reaction to assign the following reaction to one of the reaction classifications. All right, you got potassium cyanide and hydrogen chloride plus hydrogen cyanide and potassium chloride. So what's happened there? Hydrogen chloride, yep. Cl, and we've got HCN plus HCl. One way to describe this as a displacement reaction or double displacement reaction. A displacement would only be a single exchange. So if we had an element here and it displaced one of these, that'd be displacement. But since these guys are swapping places, that's a double displacement or an exchange reaction. Okay. Your authors call it exchange. I've always called it a double displacement. But they're synonymous. All right. 52. For the indicated element, select the correct oxidation number from the response list. We did that one before. Right. Sulfur in H2SO4 is +6. Right. H2SO4, 2 minus there, +1 there. So we have a +2 total for hydrogen. We have -8 total for oxygen, which gives us a -6 that has to be balanced by a +6 from sulfur. And 53. Let's see, oxidation number for carbon in potassium hydrogen carbonate. Okay. So if we do the whole thing together, we've got a -2 here, which is -6 total, +1 here, and a +1 there. That's an alkaline metal. So if we put these together, that gives us what, -4? That carbon is a +4. Okay. Excuse me, 56. Consider this redox reaction, well, maybe I better make room for it. I don't do anything special. Okay. So we got sulfur dioxide plus nitrogen dioxide yields sulfur trioxide plus nitrogen monoxide. Okay. Choose the appropriate chemical formula from the list that identifies the oxidizing agent. Oxidizing agent is the one that's reduced. So let's see. -2, -2, -2, -2. So this nitrogen has to be a +2. -6 total, that's a +6 for that sulfur. Right? SO3? Yep. And -4 total here. So we have to have a +4 there. And -4 there, +4 here. Okay. So the sulfur goes from +4 to +6, which is a loss of 2 electrons. And the nitrogen goes from +4 +2, which is a gain of 2 electrons. All right, so if we're looking for the oxidizing agent, which one is reduced? That one right there. NO2 is reduced. That's the oxidizing agent. Okay. There's 57, 58, and 59. That we're going to skip. This thing's starting to get a little weak. Get a fresh one. And 59, 60, and 61. Okay. And we'll stop on 62. Okay, for the following general reaction, choose the correct form of equilibrium constant expression. 2x is a gas plus 3y solid is in equilibrium with 2z gas. So the equilibrium constant, oops, I didn't need to do that. There we go. That's a gas, so we can use it. Concentration, equilibrium concentration, that's what square brackets mean. They also mean molarity. Square brackets to the second power divided by x to the second power. That one doesn't count because it's a solid. So that's your expression, z squared over x squared, which is b. Let's see, 63 is A. Didn't we just do that one? Oh, no. In 63, if we did 63, you'd only have Z squared. That's it. Because X is solid and Y is solid. Okay, 64. The following equilibrium, determine the effect on the position of equilibrium when some CO2 is removed. All right, remove some CO2. All right, based on that balanced equation, we're removing a reactant. All right, so the equation, and it's a gas. So the equation should shift, the balance should shift to the left. So that's B. It'll also produce some heat. Let's see, there's 65, A, and 66. Same equation, it looks like. Well, we got 66 and 67. Well, they're already on the board, so I'm not going to write them up there. What's the effect on the position of equilibrium when a catalyst is added? Catalyst doesn't change the equilibrium. It just gets you there faster, right? So it doesn't shift. C, does not shift. Same equation. What's the effect on the position of equilibrium when the volume of the container is increased? Pressure is decreased. So I guess I should write it up here now. CO2, let's see, 3H2 and CH4. And water. Okay. So we got, they're all gases. All gases. So we got 4 moles here. And we've got 2 moles here. So if we increase the volume and decrease the pressure, the equation, the reaction is going to respond in such a way as to make more moles gas. Because you're decreasing the pressure, it's going to try to reestablish that pressure. It won't make it all the way. So it's going to shift that way, make more moles. Shift to the left. Let's see, 68 is B. Let's see, stop there. Oh, that was chapter 9. That was chapter 9. We start renumbering with chapter 10. All right. So I need to change that. Chapter 10. Now we're going to start renumbering with, we're going to go down to number 3. And 4 and 5. In this reaction, Bronsted-Lowry base is, okay, got N3 minus, right? That's the azide ion, I think. H2O yields HN3 plus OH minus, correct? Yeah. The Bronsted-Lowry base. The base is the one that accepts the proton. So which one accepts the proton? It went from here to here. That's the base. And the acid would be water. It donated the proton. So N3 minus is the base. Number 4. Which of the following is not a conjugate acid-base pair? Remember what it takes to make a conjugate acid-base pair. For instance, if you have this one, then the acid, the base, would have this part of the molecule intact, and it's missing one hydrogen. Right, so which ones do that? Well, let's see, conjugate acid-base pair. You're what? Oh, it's not. Got to read my own work. Not an acid-base pair, right? So A, where you have ammonium and ammonia, that's correct. You lost one proton to get to here. B, OH minus and O2 minus. Yeah, lose that proton. Proton leaves and its electron stays behind. So that's why it goes from -1 to -2. And we lost one proton. That's an acid-base pair. H3PO4 and H2PO4 minus. H2PO4 minus. That's a valid acid-base pair. Yep. CO2 and CO3 minus. I don't think so. I mean, there's no hydrogens in there. No hydrogens to lose. All right, so that's the bad one right there. All right. 5. Which of the following pairs of acids are both members of the pair strong acids? All right. The ones that we were given as strong acids are hydrochloric, right? And these all have to be aqueous to be acids, of course. Nitric, hydrobromic, hydriodic. I don't know if we gave you those, but they're all strong. H2SO4 is a strong acid. Let's see, what else we got to choose from? That's it. Okay, so both of the members of that pair have to be strong acids. H3PO4 is phosphoric acid. It's weak. All right, so A won't work. B works. It's got this one and this one. All right. So B works. Now we found our answer. All right. Carbonic acid, C, that's a weak acid. That's what you got in pop. You dissolve carbon dioxide in water and you get H2CO3. And the last one, HC2H3O2, is acetic acid, vinegar, if it's 5%. All right, so it's weak. All right, the only one that works is B. And 6, 7, 8, and 9 there visible. Six. In which of the following pairs of acids are both members of the pair polyprotic? Polyprotic is 2 or more hydrogens. And to be the hydrogen that's acidic, it's always the first one in the formula. Right. So when you have C2H3O2, those H3s, those are not dissociable. They will not ionize. Right. The only one for C2H3O2, acetic acid, is that one leading hydrogen. H2SO4 is polyprotic, but acetic acid is not. HNO3 is not, but H2C4, H4O6 is. All right, C, we've got a monoprotic and a triprotic, right? That doesn't work. D, H3PO4 and H2C4, H4O7. Those are both polyprotics. Right? So D is your answer. Seven, which of the following is produced in the first step of the dissociation of the acid H3PO4? H3PO4, when it dissociates, and I'm going to use the abbreviated form rather than write the correct form where you transfer a proton to water. I'm just going to say this: one hydrogen and H2PO4 minus. Okay. So B, H2PO4 is produced in that first dissociation. Then you can get this one to dissociate another one, make HPO4 2 minus. You get that one to dissociate the last one and get PO4 3 minus. So you have three possible dissociations for phosphoric acid. And each time you take a hydrogen away from it, the next one becomes weaker. This is a weaker acid than that one. HPO4 2 minus is weaker than this one. And, well, PO4 3 minus is not an acid. 11, a solution with a pH of 13.3 is acidic or basic, strong or weak. Okay, 11. Yep. Let's see. pH 13.3. Okay, remember the scale. Right. Neutral is 7. Some of the most acidic we see is 1. Some of the most basic we see would be in the neighborhood of that, 13. So this is very basic. Strongly basic. All right, 12, 13, 14. Which of the following does not describe an acidic solution? All right. B, C. pH is less than 7. That's acidic. Okay. OH concentration is greater than 1 times 10 to the minus 7. OH minus is greater than 1 times 10 to the minus 7 molar. If this is greater than 10 to the minus 7th molar, then it's basic. Right. So this one's basic. All right, so we found our answer. C is the hydronium ion is greater than the hydroxyl ion. That's acidic. Yep. And the last one, OH is 6 times 10 to the minus 10. That's a whole lot less than 10 to the minus 7, which means what? Well, remember, the equilibrium constant for water is 1 times 10 to the minus 14, which is equal to hydrogen ion times hydroxyl ion. That's always the case. So if this was 10 to the minus 10, 6 times 10 to the minus 10, this one's got to be like 10 to the minus 3, something like that. So that makes it very acidic. All right, so the answer we're looking for is B. That's the basic one. And let's see, 13. If the pH of a solution increases from 3.1 to 5.1, the hydronium ion concentration does what? The pH goes from 3.1 to 5.1. Remember, the pH scale is logarithmic. Right? So when you change a whole unit, you're either going up or down by a factor of 10. Right? So we went up by a factor of 2 pH units, which would be 10 squared, or 100 times. It's 100 times less hydrogen ion concentration. It's a decrease by a factor of 100. So D is the answer. All right, let's see, 14, and we got 16 squeezed in there. In which of the following pairs of salts will both members of the pair hydrolyze in water to give solutions that are basic? All right. So our first choice is lithium chloride and sodium cyanide. And B is ammonium chloride and ammonium nitrate. And C is sodium acetate. And the other in the pair is sodium chloride. Okay. And D is potassium nitrate and lithium sulfate. Okay. So when both of these pairs are, all of these chemicals are added to water, they're all soluble, right? These are alkali metals. This is ammonia compounds are all soluble. All sodium compounds are soluble. Potassium, they're all soluble in water. So when you put them into water, you're going to get these ions that can react with water. That's where we're headed. Okay, so what do they do when they encounter water? Well, if we're looking for the ones that are going to make a basic solution, you need the ones that'll react with water plus something here and produce hydroxyls. That means this has to accept a hydrogen. Right, remove a hydrogen. So we got to transfer a hydrogen to that species, and it could have a charge on it. Probably will. It'll be a minus, right, a -1 or a -2. So you look at each one of these and say, all right, which one is going to accept the hydrogen? Well, if we're looking at only the anions, we look at the acid that the anion could have come from, right? This could have been HCl, right? This could have been HCN, HNO3, right? Because that's what you're going to get over here, H plus something. HCl, H, C2H3O2, HF, HNO3, and H2SO4. So the question asks us, which one in which will both members make a basic solution? All right, so when you add this to water, is it going to go for a hydrogen? No, it comes from a strong acid, right? Strong acids make weak bases. This is not going to take a hydrogen. Right? That's not going to make a basic solution. This one will, because HCN is a very weak acid. it makes a strong base. It's gonna latch on to one of those hydrogens and make a basic solution. So this one would be basic. But both in the pair are not. So that lets A out. And here again, right? Both of these are strong. So neither one of those is going to make a basic solution. This one, that ion right there will take a hydrogen from water, make a basic solution. This one, HF, is also a weak acid. So that fluoride ion is going to go for the hydrogen on water. Right? So that's a good prospect right there. Nitric acid again, right? That's not going to work. Sulfuric. Actually, this sulfate ion is a relatively strong base because it's derived from HSO4, which is a weak acid. HSO4 minus. Right? So this one would produce a basic solution, but this one would not. So the only one that works is this one. Now that's the chemical approach. The rule of thumb says if your salt is composed of a cation that was once a strong base and your anion that was once a weak acid, then you're going to get a basic solution. Right? So we could use that. Lithium hydroxide is a strong base, but that's a strong acid, so you're neutral. That's a strong base, weak acid. That one would be basic. This is a weak base, strong acid. This should be an acidic solution. This will be a neutral because, well, maybe not. No, this one will be acidic also. There's your sodium hydroxide, weak acid. Those are both basic. Strong base, strong acid, that's neutral. And this is strong base, weak acid. So that's basic. That's the rule of thumb way to do it. But we did it the chemical way, which is probably what I should be doing anyway. 16. If a solution is buffered at a pH of 9.5, buffer 9.5 pH, all right? Then you add a small amount of acid, will cause the solution to have a pH of approximately 9.5. It's not going to move much. Now, the key there is small amount of acid. A very small amount of acid, it'll essentially stay put. Use a large amount of acid, then it might move to 8.5, become more acidic. But a small amount, no, it'll stay right there. Now, if we had a pH meter that could measure 2 and 3 decimal points, you'd probably see it move. All right. And 17, 18, and 19, D and C, and down to A at 20. All right. Determine the concentration of an acid using an acid-base titration. Determining the concentration of an acid using an acid-base titration always involves completely reacting a measured volume of the acid with a known volume of base of a known concentration. If you're trying to standardize an acid, the base has to be a known concentration. It doesn't have to be 1 molar. It could be, but it doesn't have to be. the better answer is the base of a known concentration. Maybe you want the concentration of the base to be close to the concentration of the acid that you figure it might be. That way you're balancing equal volumes. But yeah, you need a base of a known concentration. Then you can do normality of the acid times the volume of the acid equals the normality of the base times the volume of the base. Now, if both the acid and the base are monoprotic monohydroxyl, you can use molarity here also. But if one of them is diprotic and say the acid is diprotic and the base is monohydroxyl, then normality is the way to go. Either that or write your balanced equation and then do stoichiometry. It works. Okay, let's go down to 23 is D, and then 24. Right, in which of the following pairs of acids are both members of the pair of strong acids? All right. HNO3 is a strong acid. When you reduce the number of oxygens in an oxyacid, you decrease its strength. All right, so we've gone from a strong acid, HNO3, to a weak acid, nitrous acid, HNO2. So A is not the right one. B, H2SO4 and H2SO3. H2SO3 is the weak acid. H2SO4 is strong for the first proton. Right. So B doesn't work. Hydrochloric acid and perchloric acid are both very, very strong acids. In fact, perchloric is even stronger than hydrochloric. Much, much stronger. Yeah, it's a monster acid to work with.
The hydrochloric, you've got to work. If you spill it, it's bad.
Yeah.
It's an immediate, whatever water you've got, you're pouring it on whatever you spill it on.
Yeah.
Usually yourself.
The first thing you'll notice is it starts to fume. And you can breathe the fumes and it chokes you. Mm-hmm. And then if you've got any metal around, it's going to start eating the metal.
When we do water sampling, we have to, that's the preservatives that we use, different acids for whatever we're pulling.
Okay.
And that explains why the floorboards of every single vehicle we have little pinholes in them.
Mm-hmm.
That makes sense now.
Those little droplets, they spatter.
Yeah, we use nitric every day and hydrochloric and stuff when we have to do the RPA yearly kits.
Are you preserving for
Metals.
metals? Yeah. Okay, that makes sense. Keeps them in solution. Okay, 24. So the answer we're looking for, both strong acids, is C. I used to use, I think I've told you this before, perchloric acid. It's an outstanding digesting acid for plant material. When we want to destroy the plant material and leave the ash behind and do the metal, elemental content, perchloric acid is the best. But you don't want to use it first because it's a violent reaction. If you, I may have told you this before, if you want to wreak havoc on the building, take a perchloric acid beaker, fill it up about that deep in perchloric acid. Take a nice big chunk of butter and throw it in there. Put it on your hot plate. Turn the hot plate on high, pull down the sash and evacuate the building because it will blow. Yeah. So what we used to do is take our plant material and weigh it out in each of our tall beakers and add nitric acid to it and just let it sit cold overnight. And it would pre-digest. And then we'd squirt the perchloric acid into it and turn the hot plate on, no problem. Okay, that was 24. Let's see, 26 is D, 27 is B, And 28 is B, and we're down to 29. Which of the following indicates an acidic solution? All righty. A, B, C. And let's see, pH 7.5 is basic. Just barely basic. H3O concentrations, 5 times 10 to the minus 5. 10 to the minus 5, which is less than 10 to the minus 7. Excuse me. Greater than. Get my powers backwards. That's acidic. And C is OH. OH minus is 2 times 10 to the minus 8. This is molarity, by the way. All right, so this value is less than 10 to the minus 7. So this is also acidic. 2 of the above. More than one is correct. Okay. And 31 is E, 32 is E, 33 is B. And I'm skipping a bunch. 34D, 35D, 36B. And we're stopping at 37. Let's see. Oh, true false statements. 1, 2, 3. Okay, number 1. Both members of a Bronsted-Lowry conjugate acid-base pair must contain the element hydrogen. Not necessarily. I mean, if you have a monoprotic acid, then the base is going to be devoid of that hydrogen. Right? So 1 is false. The larger the value of the acid ionization constant for an acid, the weaker the acid. No, the larger that value, the larger the Ka, the stronger the acid. So if you look at where it comes from, you've got the acid is in equilibrium with hydrogen ions plus that part of the molecule. The Ka then is equal to H plus A minus over HA. So the larger that value, the more hydrogen ions you have. That means it's stronger. All right, so this one is false. As given. That second one is false. The larger the value, the stronger the acid. Weak acids cannot completely neutralize strong bases. I beg to differ. They will. They can completely neutralize strong bases. All right, so all of them are false. All right, there are no true statements there. $38. Let's see. We'll get another one. 1, 2, and 3. Formation of a coordinate covalent bond is always part of a Bronsted-Lowry acid-base reaction. Okay. Yeah. Remember what a coordinate covalent bond is? It is a covalent bond where electrons are shared, but only one of the partners provides both of the electrons for the bond. Okay, So, if we have let's use water, for instance. It's going to produce H3O plus OH minus. Okay? So, when this molecule, say this is the acid, it gives up a proton. When it gives up a proton, what did it do? It left both of those electrons behind and it acquired a positive charge. Then it went over here and formed formed a bond with that one. It formed that covalent bond, and this one had to donate 2 electrons to that bond. So whenever you get a transfer of a proton from a Bronsted acid to a Bronsted base, it forms a coordinate covalent bond. We could put anything in here we wanted to work the same way. So the first statement is true. That one is true. The compound H2CO3 is both a strong acid and a diprotic acid. No, it's a diprotic acid, yes, but it's not a strong acid. Carbonic acid is weak. So this one's false. How about 3? The pH of a solution with OH minus equal to 1 times 10 to the minus 8 is 6. So if it has an OH concentration of 1 times 10 to the minus 6, was it? Oh, 8, excuse me, minus 8. Minus 8. Okay. What would be, we did this one before, didn't we? 14 equals pH plus POH. Didn't we do that one in lecture? Didn't do that one? Okay. All right, then let's do this then. 10 to the minus 14 equals hydrogen ion concentration times hydroxyl ion concentration. Okay. So if hydroxyl ion concentration is 10 to the minus 8, what does this one have to be? 10 to the minus 6, right? Right. Multiply these two together, you just add them together, minus 14. So now the pH of 10 to the minus 6 is equal to 6. And that's true. Number 3 is true. Okay, I should have put this. pH of that is 6. That's true, by the way. I guess I figured this course didn't call for that much depth. But it is a convenient conversion to know about. All right. 40, right? 40. Say 1, 2, 3. In aqueous solution, Arrhenius acids undergo ionization and Arrhenius bases undergo dissociation. That's true. Because an Arrhenius acid has to have a proton, and Arrhenius base has to have a hydroxyl. The association here is covalent bond. So it has to ionize. This one is an association of a positive ion and a negative ion. It simply dissociates. I know we're nitpicking, but that's the fact. So 1 is true. 2, production of the salt NaNO3 through a neutralization reaction involves the reaction of a weak acid with a strong base. Okay, if we're going to produce this one, NO3, Where did it come from? Well, theoretically, sodium hydroxide, right? Plus nitric acid. And then, of course, you'll have water. Base, acid, salt, water. Right? Both of these, strong, strong. So number 2 is false. And 3, the ion product constant for water at 24 degrees has a numerical value of 1 times 10 to the minus 14. That's true. That's just, that's the fact. So 2 of the above are true? Yeah, 1 and 3. That's correct. 41. Doing on time. You okay? We got to finish by then. I got a Zoom meeting I have to attend. I think we can make it. 41. Let's see, 1, 2, and 3. The 2 members of a Bronsted-Lowry conjugate acid-base pair will always differ from each other by 1 unit of charge. I think that's true. You have that, that's the difference of 1 charge. Even if you have this and this, that's a difference of 1 charge. Or if you have a polyprotic H3PO4 and H2PO4 minus, yeah, I'd say that's true. They only differ by 1 charge. Because when the proton leaves, it leaves its electron behind. An equivalent of an ion is the molar amount of that ion needed to supply 1 mole of positive or negative charge. That's the definition. That's the definition of an equivalent. In an acid-base titration, number 3, the indicator changes color when the reaction between it and the added acid is complete. In acid-base titration, the indicator. Yes, what they're saying is when you titrate an acid and a base, you want an indicator that'll change colors when you've reached the equivalence point. The equivalence point is when hydrogen ions and hydroxyl ions are equal. They've all neutralized each other. And that equivalence point you want to be indicated by an end point, a color change. So 3 is true also. Oh, they're all true. All 3 statements are true. 42 is B. 43 is D. 44 is A. And we'll stop at 45. Okay. Let's see. 1, 2, and 3. All rainfall, even in unpolluted areas, is acidic. That is true. If you have a pristine, uncontaminated air mass through which water falls, it's going to pick up carbon dioxide from the air. And when it does, it will produce H2CO3, carbonic acid. So water falling through the air is going to be acidic. It won't be much. It'll be like 6.4 or 5. Maybe a little lower now with an increase in CO2 in our atmosphere, but it'll be in that neighborhood. Okay, 2. Blood plasma, interstitial fluid, intracellular fluid, the three general types of body fluids, all contain electrolytes. Yeah. What's an electrolyte? It's operationally defined. Anything you put in the water that will allow water to transmit a charge. Right. Pure water is an insulator. You stick your electrodes into pure water, your light bulb won't turn on. But if you have an electrolyte in there, something, a charged ion that will transfer, complete the circuit. And all those body fluids have electrolytes in them. Blood plasma is slightly acidic because ions it contains undergo hydrolysis. No, that's false. Blood plasma is slightly basic. And it doesn't have anything to do with that hydrolysis thing. It has to do with buffering. Your blood plasma is buffered. Actually, it's a very complex buffering system. And it'll be in the neighborhood of 7.35 to 7.45. Very, very narrow range. Anything higher than that, you're basic. Anything lower than that, you're acidic. Which is the dangerous side for diabetics. Right, if they go ketoacidosis, get them to the hospital quick. Because their body can't use glucose. Their cells won't take it up. If they go into diabetic shock, it's because they've got a lot of glucose in their system and the body can't use it. So it goes and uses other things, ketones in particular. And when it oxidizes ketones, you make acids. And then the pH goes. I remember a TV show, the first episode was Danny Thomas. Remember Danny Thomas? No? Okay, he was famous. Anyway, he was a doctor in the show, and he just opened his clinic and had no furniture. So he had two boxes in his examining room, one for the patient, one for him to sit on. So this guy came in who was feeling really, really bad. So he sat him down there and he looked at him. He leaned over and smelled his breath. He says, "You get to the hospital. You're in diabetic shock." What he smelled on his breath was acetone. Acetone is a product of those alternate reactions. If you can smell acetone on somebody's breath, and they haven't actually been breathing it, then they need to get to the hospital. Or if you have a glucometer, check their blood sugar right away. If you can smell acetone on their breath, I bet their glucose level is going to be 400, 500, 600, which is dangerous. Okay, so two are correct. B. Sometimes TV shows get it right. I tried to watch Breaking Bad, binge Breaking Bad. I made it through about the first 4 shows. It was just painfully slow. So I said, plus their chemistry was just a little bit off. All right, got those B, B, and C for 46, 47, 48, and we'll stop on 49. Now, Bryan Cranston's a good actor. Really, I've seen him in a bunch of stuff. He's an excellent actor, but the show.
It gets better after you watch a few episodes.
Does it really? Okay.
I really like it.
I'll try again then, when I have time.
If you want something funny, try Resident Alien. It's on season 3, I think,
Oh, okay,
and it's hysterical.
okay. I've seen little clips, and the guy that's the alien looks like he's probably got the comedic timing down.
Oh, it's perfect. It's perfect.
Okay, select from the following list, compound or ion best fits the description. Reacts with H3O to form HPO4 2-. Okay, if it's going to react with H3O plus and produce HPO4 2 minus, HPO 2 minus. That means it's probably going to pick up a proton from this one. And that would give you water on this side. So the proton would have to go to something that would have PO4 in it and be missing that hydrogen. Like that. That way this hydrogen transfers over there and gives you this product, lose the hydrogen here and gives you water. Okay. So D should be the answer, PO4 3 minus. That looks like a 5, doesn't it? 3. All right. 50, 51, and 52, B, C, and A. And we're gonna keep going, 53, 54, and 55. Okay, 54. Select 54, select from the response list for the acid that best fits the description, an acid that has more non-acidic hydrogens than acidic hydrogens. Okay, the non-acidics will be the ones anywhere in the molecule that's not first. Right. So if we look at each one of them, A, of course, can't be it because it has no non-acidic hydrogens. B is acetic acid. It has 3 non-acidic and 1 acidic. Right. So B is the answer. C, of course, has 2 non-acidic and 2 acidic, and sulfuric acid has nothing. So acetic acid is the best answer. And that's why sometimes we draw it like this. That's the same molecule, acetic acid. And there's the acidic proton right there. These guys right here are too tightly bound to carbon. They will not dissociate, ionize. Not without a lot of help. But you just throw it in water, this is the only one that goes. All right, that was 54. 55. Select from the response list acid that best fits, an acid that completely dissociates in solution to produce negative ions with a charge of 1. Completely dissociates, that's the key. We're looking for a strong acid that completely dissociates in solution to produce a negative ions with charge of 1. Okay, we know that B and C are weak acids. Right, so they're not going to be candidates because they don't completely dissociate. HCl is the best answer, but H2SO4 is an if. Because H2SO4 is strong when it does this. It completely dissociates to produce that. So it produces negative ions with a charge of 1, yeah. But I think what the authors are getting at is it also partially goes to this one. Right, so you still have some 2 minuses floating around there. That's why in a multiple choice test, pick the best answer. Okay, 56. Okay, select from this list a salt whose dissociation produces equal amounts of 2 ions. So we're looking for a salt and soluble, completely soluble. So where do we have salts here? All right. KOH is not a salt, it's a base. Sodium nitrate is a salt. And it will completely dissociate into sodium ions and nitrate ions. That works. H3PO4 is an acid. K3PO4. Oh, this also produces equal amounts of cations and anions. But when we completely dissociate this one, this produces 3 potassiums for every 1 phosphate. Right. So they're both soluble, but they don't produce the same number of ions on each side. 1 to 1, this is 3 to 1. Right, so there's your answer right there. Sodium nitrate. Oh, wait a minute. Yeah, that's right. I was there for an instant. I look at 57 and say, what? No, it's not it. It's a different question. Oops, go too fast. 58, 59 is C, 60 is D. 61 is A. 62 is C. 63 is B, 64 is B. 65, 6 and 7, A, C, and B. '68 is B. And then we're down to 69, 70, and 71. What is the pH of a buffer that is 0.25 molar in a weak acid? So our weak acid, excuse me, our weak acid is 0.25 molar, right? And the conjugate base of that acid is 0.26 molar. Okay. What else are we given? The pKa for the acid is 5.53. pKa equals 5.53. This is where you're going to use the Henderson-Hasselbalch equation. And that is pH equals pKa plus common log of the conjugate base divided by acid concentration. And so we put 5.53 here, 53, and then we have the log of, let's see, on top we have 0.26, and the bottom we have 0.25. Okay. I guess I need the calculator. Let's see, 0.26 divided by 0.25. Nope, that's not right. 0.26, 25. That's better, 1.04. All right, this is 1.04, then we'll take the log of that. 1.7 times 10 to the minus 2. 703 times 10 to the minus 2, and we add that to 5.53. Which is rounded off to 2 places is 5.55. Is that a selection? Yeah, C. Okay. I don't know what to tell you about that. Does that review document have useful information in the back? Yeah, but it doesn't have Henderson-Hasselbalch. Okay, I'll tell you what. In case it shows up, I think that's the only formula that we really have to remember for this one. So just write it on a card and keep it with you for the test. Okay. And then you might need a periodic table. Okay, that was the last one, wasn't it? Yeah,